Hello everyone, and welcome back to Math 220A Mathematical Logic. Lecture 16, Ultrafilters and Ultraproducts. Today we introduce an important model theoretic construction which allows us to take an average of a given family of functions. More precisely, idea: assume we are given mi for some I in an index set capital I, all L structures in some given language L. Then we want to consider or to define a structure M in the same language, so an L structure which is the average, in quotation marks, of the mi's with respect to some measure, in quotation marks, on the index set I. More precisely, we would like to say that a certain formula holds in this average structure M if and only if it holds on a large set of the structures mi in this sequence. Of course, in order to really define the truth value, in M, large must somehow correspond to measure 1 as opposed to measure 0, so that we wouldn't get the intermediate truth values for the formulas in M, because every sentence has to be either true or false in M. So in order to accommodate this, we have to begin the discussion with a particular kind of measures which only give values 0 or 1 to all sets. So every set is either almost everything, full measure 1, or almost nothing, or measure 0. This is nicely formalized by the notion of ultrafilter, and more generally we will start with a discussion of filters. And at the end we will apply ultraproducts to give a new, purely semantic proof of the compactness theorem for first-order logic. So before we deduced it as a corollary of the completeness theorem, which had this whole recourse through formal proofs, but now we will give a purely semantic method to prove it, which does not involve the notion of formal probability at all. So let us begin with the definition of filter. Suppose I is a non-empty set, then a subset F of the power set of the set I, so a collection of subsets of I, is called a filter on I if we have the following axioms. 1. I is in F and the empty set is not in F. 2. If A and B are both in F, then their intersection is also in F. And 3. If A is a subset of B and A is an element of F, then B is also an element of F. So intuitively we should think about the sets in F as the large subsets of I, and so in particular we want all of I to be a large set, of course. An empty set shouldn't be large. The intersection of two large sets should be still large, and also if any set containing a large set should also be large. So this is the intuition behind this definition. A couple of examples of filters. One, we can consider all sets of the form R minus X, where X has Lebesgue measure 0. So all sets whose complement is measure 0 is a filter on the reals, on the set of the real numbers. 2. Suppose I is any infinite set and kappa is an infinite cardinal such that kappa is less or equal than the cardinality of the set I, then we can consider all sets of the form I minus x, where the cardinality of x is less than kappa. This is a filter on I. In particular, the set of all cofinite, so sets whose complement is a finite set, subsets of I is a filter called the Fréchet filter on I. And finally, we have a trivial example of filters on a given set. So suppose that I is any non-empty set, then by a principle, filter on I, we mean a filter of the form A is a subset of I, X is an A for some fixed element X in I. So we can consider the collection of all sets which contain a given fixed element, then such filters are called principal. Definition: an ultrafilter on I is a maximal filter on I under inclusion. So it means there is no way to add another set to the collection of sets in the ultrafilter so that it remains a filter. So i.e. a filter not properly contained in any other filter on I. Example: any principal filter is an ultrafilter Indeed, any larger filter would contain a set that does not contain a given particular element x and has hence its intersection with the set consisting of x alone, which must also be in the filter, would be empty, contradicting the fact that the empty set is not a member of any filter. While it is rather difficult to describe any particular non-principal ultrafilter, they do exist thanks to Zorn's lemma. So we have theorem: any filter f on I extends to an ultrafilter on I. Proof: let S be the set of all filters on I containing F. Now note that the union of a chain of filters is a filter so by Zorn's lemma, which remember is equivalent to the axiom of choice, but in fact we are using just this weaker form, by Zorn's lemma, we can find the maximal element in S under inclusion, which is then indeed an ultrafilter on I. Note that if F is the Fréchet filter on I, then any ultrafilter on I extending it is non-principal, indeed it cannot be principal, as for any x, an element of I, the set I without the point x has to belongs to the Fréchet filter by definition, which is a subset of U, so it has to belong to U. But of course then its intersection with the set consisting of a single element x is empty, so it cannot be a filter then. So in particular this shows that the axiom of choice implies that on every infinite set there exists a non-principal ultrafilter. The following lemma gives an equivalent characterization of ultrafilters. So a filter U on I is an ultrafilter if and only if for every A subset of I we have that either A is in U or the complement of A is in U. Proof. Consider the right to left implication. If U is properly contained in some filter F, then there is A which belongs to F but not to U. But also, since F is closed under intersections, and does not contain the empty set, we must have that the complement of A is not in F, because otherwise the intersection of A with its complement is, of course, would be empty. Hence, we have that neither A nor the complement of A are in U, which of course contradicts the assumption. So this gives us the implication right to left. Now left to right. Suppose U is an ultrafilter on I in the sense of our original definition, so it's a maximal filter. But assume also that some given set A, subset of I, is not in U. Then we can consider F to be the collection of all x contained in I, such that Y minus A is a subset of x for some Y, an element of U. Then one checks that F is a filter on I containing U. Hence, by maximality of U, we have that U is equal to F, but the complement of A is in F by the definition of F. So we conclude that for any set A such that A was not in U, we get that the complement of A is in U. So this shows the left to right implication. Remark: an ultrafilter on I is the same thing as a finitely additive zero one valued probability measure on the Boolean algebra of all subsets of I, where a set is in U, so ultrafilter U, the set is in U corresponds to saying that the measure is 1, and the set is not in U corresponds to measure 0. Having defined ultrafilters, which correspond to our measures with respect to which we want to take the averages of structures, we can now define this averaging construction, namely the ultraproducts. So let L be a language, I an infinite set, and let Mi be an L structure for each I in the index set capital I. Let U be an ultrafilter on I. Then the ultraproduct of the structures Mi, I and I, with respect to the ultrafilter U will be the L structure M defined as follows. First, the universe or the base set of the structure M is the set given by the direct product of the MIs modulo E, where E is the equivalence relation given by F is equivalent to G if the set of all indices I and I such that F of I is equal to G of I is in U. So here first of all note that we have U in the direct product of structures as the collection of all functions F from I to the union of the MIs I and I such that the value of the function f of I is an element of the structure Mi. So the usual notion of the direct product of sets, Cartesian product of sets. So hence we look at the base set of the structure M is going to be the classes modulo in this direct product, modulo the equivalence relation E, defined by saying that two functions are equivalent if the set of indices on which they agree is a member of the ultrafilter U. And we leave it as an exercise to check that E is indeed an equivalence relation. Two, for every constant symbol C in the language L, we set the interpretation of the symbol in the ultraproduct M to be the E-class of the sequence given by f of I is equal to the interpretation of the same constant symbol C in the structure Mi for each I in the index set capital I. 3. For every function symbol f in the language L and any g1 through gn where n is the arity of the function symbol f in the direct product of the Mi, I and I, we define the interpretation of the function symbol f in M on the classes corresponding to these elements, to these representatives g1 through gn, to be the element g mod e, where g is the function from I to the union of the Mi, I and I, defined by g of I is equal to the interpretation of the same function symbol f in the structure Mi applied to the value of the function g1 on I through the value of the function gn of I. And one can check that this definition does not depend on the choice of the representatives g1 through gn of the corresponding E-classes. So again, this follows using that U is an ultrafilter on I. And finally, for every relational symbol R in L of arity n, we define the interpretation of R in M to be the subset of M to N as follows. So for all g1 through gn in the direct product of the MIs, we will say that the corresponding classes g1 mod e through gn mod e belong to Rm if and only if the set of indices I and I such that the corresponding coordinates of these functions, so g1 of I through gn of I, which is of course a tuple in the structure Mi, belongs to the interpretation of the relational symbol R in the structure Mi. So the set of those indices for which this corresponding coordinates belong to R is in U. So it's a large set with respect to the ultrafilter. Again, check that this does not depend, this definition does not depend on the choice of the representatives of the E-classes. Using the properties of the ultrafilters. In this way, we obtain a well-defined L structure on the corresponding base set M, the collection of all equivalence classes of the sequences with i's coordinates in the structure mi, and we will often denote the ultraproduct of a sequence of structures mi with respect to an ultrafilter U on I by writing that M is equal to the product of the Mi I and I modulo ultrafilter U. First, we note that if we start with a principal ultrafilter U, then the ultraproduct construction with respect to it doesn't produce anything new. Lemma: suppose Mi I and I is a collection of L structures. Assume that J is an element of the index set I, and let Uj be the principal ultrafilter generated by the point J, so it consists of all X subset I, such that J is an X. Then the J's projection map pi, which sends the direct product of the mi's to the J's coordinate, so we are forgetting all but the J's coordinate. Then this map pi induces an isomorphism of L structures from the ultraproduct of the mi's with respect to U to the structure Mj. Proof: note that for a set X subset of I, we have that X is an U if and only if we have that J is an X, of course, since U is a non-principal ultrafilter on J. So we have Uj, by the way, everywhere to keep the notation consistent. So if we have that G is E equivalent to G prime for some two functions G and G prime in the direct product of the structures, then we have that their values on the coordinate J are the same. So we have G of J is equal to G prime of J. Hence, pi induces a map from the base set M of the ultraproduct to Mj. Just because two elements are equivalent, are in the same class, so represent the same element of the ultraproduct, if and only if they have the same Jth coordinate. Now, it is clearly surjective, and we can check that it is an L embedding from the definitions, by unwinding the definitions. Okay, so this example shows that taking an ultraproduct with respect to a principal ultrafilter simply produces us a structure which appears in the corresponding position in the family Mi. The next result is the theorem of wash, which explains how to determine the satisfaction of a formula in the ultraproduct in terms of the index set of the structures Mi in which it is satisfied. So suppose we are given Mi, I and I, a sequence of L structures and suppose that M is the ultraproduct of the MIs with respect to an ultrafilter U for U an ultrafilter on the index set I. Now let phi of x1 through xn be an L formula, and let g1 through gn be some elements of the direct product of the structures. Then we have that the ultraproduct M satisfies phi on the element g1 mod E through gn mod E if and only if the set of indices I in I such that the structure Mi satisfies phi on the corresponding coordinates of the sequences, so g1 of I through gn of I is in the ultrafilter U. In particular, applying these two formulas in zero free variables, we get that for an L sentence sigma, the ultraproduct M satisfies sigma if and only if the set of those indices I and I, such that Mi satisfies sigma, is in the ultrafilter U. Proof. First, we observe that if T of x1 through xn is an L term and g1 through gn are some elements of the direct product of the MIs, then we have that the interpretation of this term in the ultraproduct applied to the classes of the GIs is equal to G, some other element of M, if and only if we have that the set of I in I such that the interpretation of the term T in Mi evaluated on G1 of I through Gn of I is equal to the ith coordinate of G is in the ultrafilter. The claim follows by induction on the height of the term T using the fact that the corresponding statement for the function symbols themselves is true by the definition of ultraproduct. So the height 0 case is given by the definition of ultraproduct, and then by induction on height we show that it holds for arbitrary terms as well. Now given this, the proof is an induction on the height of the formula phi. The atomic case is an immediate consequence of the corresponding result for terms that we just established, and the inductive step for the conjunction and the negation is easily verified using the properties of the ultrafilters. For example, if we have a formula of the form phi of x bar and psi of x bar, then we can consider the set x phi to be the set of all I and I such that mi satisfies phi of g1 of phi through gn of phi, and similarly we define x psi to be the set of indices I and I such that the structure mi satisfies phi psi of g1 of phi through gn of phi. Then by the inductive assumption we have that m satisfies phi of g1 mod e through gn mod e if and only if we have that the set x phi is in U. Similarly we have m satisfies psi of g1 mod e through gn mod e if and only if x psi is in U. Now if we let x phi conjunction psi to be similarly defined as a subset of phi consisting of those indices for which the conjunction is satisfied on the corresponding coordinates in the corresponding structure mi, then we have that x phi conjunction psi is equal to the intersection x phi intersected x psi. And since ultrafilters are closed under intersections and supersets, we have that x phi conjunction psi is in the ultrafilter U if and only if x phi is in U and x psi is in U, for which we already know by the inductive assumption that this happens if and only if m satisfies phi of g bar mod e and psi of g bar mod e. So it satisfies the conjunction. Similarly, we treat the case of adding a negation in front of a given formula using that if x phi is not in U, then the complement I minus x phi is in U. So this is the property of the ultrafilter which guarantees the negation step. So it remains to consider the case when phi is of the form exists y psi of xy, where x is allowed to be a tuple of variables. Now, by the inductive hypothesis, we have that m satisfies exists y psi of g1 mod e through gn mod e y if and only if there exists some element f in the direct product of the mi's such that the corresponding set xf, which we take to be the set of all I and I, such that mi satisfies psi of g1 of I through gn of I, f of I is in the ultrafilter U. But now xf is contained in the set Y consisting of all I and I, such that the structure mi satisfies exists y psi of g1 I through gn I y. And since ultrafilters are preserved under supersets, it follows that if M satisfies exists Y psi of G1 mod E through Gn mod E Y, then Y is in U. Conversely, suppose that Y is in U, then for each I in Y, we choose an element AI in Mi, such that Mi satisfies psi of G1I through Gni AI, and we also define a function f, so an element of the direct product of all structures Mi, by setting f of I to be AI for I an element of Y and fi in Mi arbitrary for I not in Y. Then, with f chosen in this way, we would have xf will contain Y, and hence we will have that xf is an element of the ultrafilter U. So, by the above equivalence, this means that M satisfies exists Y psi of G1 mod E through Gn mod E Y. So this concludes the proof of Walsh's theorem. As a corollary of Walsh's theorem, we can give a different proof of the compactness theorem. So for any theory T, if every finite subset of T has a model, then T also has a model. To prove the compactness theorem, we will pick a model for each finite subset of T, and then we will consider a certain ultraproduct of the structures, hoping that it will provide a model for the whole theory T. So proof, let T be an L theory such that every finite T0 subset T is consistent. Let us take I, the index set, to be the set of finite subsets of T. Now for each I in I, let Mi be a model of I, so a model of this finite set of sentences from T. Also, for each I in I, we let xi, a subset of I, be the set of finite subsets of T extending I Note that the set xi I in I does not include the empty set. So namely for each I, the set xi is non-empty, because we can find many finite subsets of T extending it by adding just one more sentence, for example, from T. On the other hand, it does include the whole set I, because we have that I is equal to X empty set. And also note that the collection Xi for I and I is closed under intersections. As we have that Xi intersected Xj is equal to Xi union j for any ij in I. Sets of sentences from T which extend both I and both j to given sets of sentences, of course also extend the union of this set of sentences. So we have these properties, hence if we take F to be the set of all X subset of I such that X contains Xi for some I in I is a filter on I. By Thorne's lemma we know that there exists U, an ultrafilter on I, extending F, so U is a subset of F. Now we let M be the ultraproduct of the MIs with respect to U, this ultrafilter. Then we claim that this structure M is a model of T, so it satisfies all of the sentences in T simultaneously. Let us prove the claim. So assume that sigma is an arbitrary sentence in the theory T. If we have that J belongs to X sigma, that is, if J is a finite subset of T containing sigma, then the structure Mj satisfies sigma, since by the choice Mj satisfies J. Hence, if you look at the set of all I in I, such that Mi satisfies sigma, we see that this set contains the set X sigma, and we also know by the construction of the filter F that X sigma is an F. So of course also X sigma is an U, since U is an ultrafilter extending F by construction. So the set of all I in I such that Mi satisfies sigma is an U. But now, by Walsh's theorem, it follows that the ultraproduct M also satisfies sigma. And sigma was an arbitrary sentence of the theory T, so we conclude that M realizes all sentences in T. So this concludes the proof of the compactness theorem.